Hello, it's Keith here, and this is lesson 96 of the platform-specific series of my Z80 assembly programming tutorials, and we're looking at the ZX Spectrum again, and we're looking at MaxTile. Wait, I hear you say, didn't we look at that last week? Well, we did, but we have a different version this time. Last time, the version used 8 byte per pattern tiles, and this version uses 9, with the 9th byte being a color attribute, so our tiles are colored this time. So the difference is obviously the screen is more colourful, but the code is a little bit more complicated. There's extra code to do the colour attribute, and it's not so easy to calculate the memory address offset of the tiles, because now we need to multiply by 9 rather than by 8, which is a little bit harder. Our bit shifts become a little bit more complicated, but this is what we got. It worked quite nicely, and obviously people do like their colour for good reasons. So that's what we got today. We're going to go over to the code and we're going to take a look. Now, I'm not going to assume you've seen the last episode with the black and white version, but it would help out. I'm going to go through some of the bits a bit quickly, simply because I'm getting quite bored of discussing them, if nothing else. Anyway, so here is our example today. We are looking at MaxTile Color Mid. This is the example that we're running, and that uses the ZXS MaxTile Normal Color ASM. This is the color version of the tile drawing routine. The code itself hasn't changed too much. MaxTile, if you don't know, has 3 caches that it uses to cache the draws that are about to be done to the screen. Each is 256 bytes. So we're defining them here. The memory addresses aren't quite right because those are 512 spaces. Testing, I was allocating extra space in case things were going wrong, but they don't. So this could be C2, C3 and C4. That would work fine. But anyway, we've got a lookup table for the Xflip. The Yflip is done in real time. It doesn't need a lookup table, but the Xflip is a little bit complicated, so we have a lookup table. And then the other thing I want to show you is the screen base. We're defining the VRAM screen base here of the bitmap data at 4000 there, and that is used for when we're drawing the tilemap to the screen. We use that screen base. When we're drawing the simulated sprites of the screen, it's still the same tilemap code, and we calculate an offset in a way we'll look at in a moment. Okay, the do enable interrupts doesn't execute on this system. On systems where interrupts turn back on, there would be an EI command here that isn't on the Spectrum, because the Spectrum interrupt handler uses I think it's the IY register. My code uses IX and IY, so if we turn that on, we'd probably get a crash. Wouldn't go so well. So that's why we're disabling interrupts here. And then we've got our code. Now, at the end of our code, you can see we have the pattern data for the tiles here at memory address 9000. Now, each of these tiles is 9 bytes this time. So we've got different bitmap source data here. And we're calculating the offset for tile number 128 here. And that has been done by simply 128 times 9 equals 480. So this starts at 9480. And that's so that our character tiles are at the correct positions for the tile maps that define those simulated sprites. So that's what we've got there. So here we've got our fill pattern data. This is where just 2 bytes are used alternatingly to fill the background tiles. You can see those fills, those solid colors there. That's been changed this time. We're using 2 bytes for the bitmap data, but 1 byte for the color attribute. So these are 3 bytes each this time. And we've got a spacer here just to make sure the tile numbers align correctly, because if they don't align correctly, when we get our bitmap data for the other sprites, everything will go wrong and things will end up quite weird. So that's why we're spacing that fill data out correctly there. So that's what we've got there. Now, as before, exactly unchanged, we have the Xflip lookup table. So what this does is we define this in memory, and the bottom byte needs to be 0 for the first entry in the lookup table. And what we do is we basically use the L byte in the HL address as the source byte that we want to flip. And then we flip all of the bits, and effectively all the pixels, because 1 bit per pixel on the Spectrum. We flip all of those into the opposite position horizontally. So this bit over here is shifted over here, and then the next one along becomes the next one along, and so on and so forth across the byte. So we're doing that, and then we store that flipped byte in the same position in the lookup table as their L byte that we flipped. So we flip the L byte and store the result in the HL destination. And what that means is when we want to Xflip a byte, we simply load the H byte with the address of our fliplet, the L byte with the byte we want to flip, read a byte from HL, and that is the flipped equivalent of the byte we wanted to flip. It's pretty fast. It's the fastest way of flipping data, basically. So that's what we're doing there. We've got other code, which is the test code. We're not really going to cover that here. Please, if I've got an entire series on MaxTile on the multi-platform elements. It's just the platform-specific parts we're looking at today. And one important thing is MaxTile is pretty complicated. If it's too complicated for you, just ignore it. Just forget all about it. Just use the draw tile routine as a basis for your own code, because this is going to draw an 8x8 sprite or tile, if you will, to the screen, and it supports Xflip and it supports Yflip and a few other tricks that maybe you want to learn from. So just use this on its own, maybe. Okay. Anyway. So when we're drawing our tilemap to the screen, we just start from the top left corner of the screen, which is that screen-based parameter we defined earlier. However, when we're drawing a movable object like that, moving Chibico going down the screen there, we need to use the getScreenPos routine. This takes an X and a Y coordinate and it converts them into a VRAM destination. Now, this is the bitmap data for starters, and the X and Y coordinate are in logical units. Now, in all of my tutorials, all the modern tutorials, I use logical units, which is pairs of pixels, and this is because a 256 by 192 screen becomes 128 by 96 logical units, and that gives us a buffer area around the screen for off-screen areas without going over a single byte. So very convenient for X and Y coordinates. So that's what we've got, and we're basically converting them here. We're taking the X coordinate and converting it to a number of bytes, and the Y coordinate we are having to break up the line number because the VRAM destination, the bits of the HL address are made up like this, and the Y bits here, Y 3, 4 and 5, are the bits 3, 4 and 5 of the Y line in lines, not logical units. So this is a bit of a pain, generally speaking, but this code will calculate the VRAM destination correctly, adding the screen base, which is assumed to be 4000. It might not be if you're on the Spectrum 128, so that's why it's got a self-modifying code option there to change the VRAM destination in case you're using hardware double buffers. But anyway, now here is the draw tile routine. Now the tile map is in memory address BC, and it's 2 bytes per entry in the tile map with the MaxTile. MinTile uses a single byte, MaxTile uses 2 for the extra functionality. The bottom bit is an update flag, so we don't redraw everything if we don't need to. If nothing's moved, if the screen hasn't scrolled and the sprite hasn't changed its position, we don't need to redraw the background tile map. But when we do, we need to know what we're going to draw. So rather than have a cache and the source data like we did with the MinTile, MaxTile uses 2 bytes per entry, and the bottom bit is an update flag. Now, if we're running this routine, the update flag was set, because otherwise we wouldn't be running the draw tile routine. And so as part of that, the bottom bit of the 2 bytes, or the first byte that's been loaded from the tile map, has had 1 bit shifted out of the right-hand side, the update bit. And the reason we've shifted it out is we're going to shift a 0 back in a moment so that we don't redraw this tile next time. Just something important to understand at this point. So, okay, so here we're checking the next bit, which was bit 1 and is now bit 0, and this is the program bit. Now, the way MaxTile works is it's a sort of tree structure. The most common, simplest tile is the most likely to be executed, and so it's got the shortest path to execution. The more complex, rarer ones have more branches, which takes longer, but it means that we focus on the most likely fastest one, which is the unflipped tile. So if the program bit is not set, this is an unflipped tile. We are then shifting a 0 into the update flag and writing it back to the tile map. We are then clearing all of the bottom bits because they relate to the kind of program, which there isn't one in this case. Now that effectively multiplies the tile number by 16. That's because this code MaxTile is designed for 4 color sprites, which would mean 16 bytes per tile pattern. However, this one uses 9 bytes per tile pattern. A bit tricky there. So we're loading the L byte there, getting the second byte, which is the remaining bits of the tile number there, and getting that into H. Okay, so that's multiplied by 16, effectively the tile number. So we now want to shift that to multiply it by 8. So we're shifting it to the right by 1 bit. That's effectively a multiply by 8, and we store that value for later in a temporary memory entry there, because we want to multiply by 9. And the way we do that is we multiply by 8, multiply by 1, and add those two together. And so we've got the value by 8 in that temporary value there. We now shift again 3 bits to the right, and that is now effectively multiplied the tile number by 1. We then add that to the entry in that temporary value we just stored, and we have now effectively multiplied by 9. That is the offset to the tile pattern data we want to show to the screen. So what we do next is we add the tile pattern data address, which is in DE when this routine is executed, and then we use stack misuse, and so we move that into the stack pointer. That means we can pop off the data from the stack and we get the tile data that we want to draw to the screen. Okay, Now, this is our main drawing routine, and if you saw last time's episode, you will recognize the first part because it's identical. Okay, so we're backing up the H entry in the HL VRAM destination. In the shadow registers, HL will be the VRAM destination. We pop 2 bytes off our source data, off the tile pattern data, and we write the first byte to the screen, move down a line. We just ink H to move down a line. That is the benefit, one of the benefits of this weird layout in VRAM. We ink L to move across the screen, ink Y to go down the screen within an 8-byte boundary, and then it gets tricky. But because of the alignment of this code, we never have that tricky part to worry about. We're relying on the tiles being 8x8 boundary aligned with this code. So we're doing those bytes, doing all of the lines of this tile. At this point, we've now done the bitmap data, and that's where the last example ended. However, this time we're going to draw color information to the screen as well. Now, we've got H and L as our VRAM destination for our bitmap data, and what we're going to do now is we're going to tweak it, and we're going to convert it into the VRAM destination for the color data. Now, if you remember here, basically you've got 0, 1 and 2 here are the bits, are the offset within a tile. Now, the remaining bits, the bits here and the bits here, are effectively the strip down the screen. And so if we remove these 3 bits here and shift these bits along, what we will effectively end up with is the offset to the color information for the tile that we just drew, and that's exactly what we're going to do here. So we're shifting the H bit to the right 3 times here, and then we're ORing in 58 here because the color information starts from 5800. If you were using a different screen base, you would need to change that, but in this case that is correct. What we're then doing is we're getting one last byte. We have to pop 2 bytes off the stack, but we want one last byte, and that is the color attribute byte there. So that is setting the color attribute for this tile, and that's all we've got. Now, I've actually put a label here because we're going to reuse this code, because a lot of the routines use this exact same code. All of them actually do, one just very slightly differently. So we're going to see that being used over and over again. That's the bulk of the difficulty for this version of the code. There is a bit of a tweak with regards to the double height tiles, but you'll see that in a moment. Now, as I said before, up here we were checking to see if we needed the advanced code to draw our tiles to the screen. If the advanced code is needed, then we end up here, and what we're doing here is we're checking if the X and Y flip are both 0, if the X flip and Y flip are both 0. This is what's referred to as custom code, and this is special code for doing custom kinds of tile. So Xflip and Yflip is sort of considered to be standard effects, if you will. Okay, so if we're X-flipping or Y-flipping or both, then what we need to do is we need to do the same thing as before, calculate the offset of our tile number here. That's what we're doing here, multiplying by 9 once again, adding D and E here, so SP now contains the source pattern data exactly the same way as before. And then what we're doing here is we're going to see what bits are set. So if we've got to this point, then some bit is set. So what we're checking here is if the Y bit is set, and if it's not, then only the X bit is set, and so we're doing an X flip. As I said before, we've got that lookup table. We're going to use B and C to point to the lookup table. So we load the B byte, the B register, with the top byte of the lookup table. Now what we do is we set the C byte to the byte we want to flip, and we read in from memory address BC, and that will be the flipped equivalent of whatever we put into C. And that's what we do here. So we pop D and E, the pattern data. We take the E byte and we load that into C, and then we load in from BC. We've just got the flipped equivalent of that E byte, and then we write that to the screen, move down the line, load C with D, load A from BC, that's the flipped equivalent of the D byte, and we write that to the screen, and we keep moving down the screen until we get to the end. Now the only change here is once we want to do the color information, last time we used the C register as to remember the original value of H. Well, we didn't do that this time because we used BC for other purposes, so we're updating C here so we can share that same piece of code, give it the C register that it expects, and then that's it. So that's our X-flip routine. Our Y-flip routine, well, that's all the way down here. Here it is. So all that's doing here is checking the X-flip flag, because it's possible here that both X and Y flip are set, and if it is, it's branching over to this version. Y-flip's even easier. All we do is we start drawing to the the screen from the bottom and move upwards. We read the pattern information in the same order as before, but we draw it to the screen in reverse order. Very easy, and that's what we're doing here. So you can see we're just drawing the data and then doing the color byte as before. Very straightforward. And the XY flip, well, that's not particularly complex once we know those two tricks. We're just doing them both at the same time. So we're moving to the last byte of the screen data here. We're using our lookup table. We're flipping our bytes, and we are basically going backwards, moving up the screen. And again, once we're done, we're drawing our colors to the screen there. So again, pretty straightforward there once we know the tricks that we're going to do. Now this just leaves the so-called custom tiles, and these are the sort of special programs to do special kinds of tile, and they're designed for things like speed-ups mostly. So we've got a few kinds of tile. So we've got a fill tile. That's a tile filled with entirely 2 bytes. That's fast, very fast. A double height tile. Now this was designed to save memory, because if we draw 2 lines with the same bitmap data, we've effectively got an 8x4 pixel block. Then it's a little bit low resolution, half the resolution, half the memory, and if we're running out of memory, that gives a nice effect in a lot of cases. If your tile is basically a vertical column, you won't even notice the difference. So I'd say definitely worth having. Now this becomes a little bit tricky though, because we're using the same tile data as our normal graphics. If you look at the example code here, you will see, if I compile the right code, if you look at the graphics code here, you will see here, if I move my player out the way, that kind of rabbit ear fellow there is the same data as that. It's literally the same pattern data. It's not an alternate version, it's the same data. Now this causes a bit of a problem because of that pesky 9th byte. So what we're doing here is we're calculating the offset to our tile pattern data here, multiplying by 9 here. But then what we need to do is we need to consider whether we're being asked to draw an odd or an even tile, because basically if we are being asked to draw an odd tile, so tile number 1 or tile number 3 for example, we need to move down to the second half of that tile pattern, and we can't just multiply by 4 like we used to, because the color information, there isn't a second set of color information at the half tile point. So what we're doing here is we're then offsetting by 4 bytes for the odd tile numbers here, and that's to get us to the correct bitmap data. We're then drawing the bitmap data to the screen in the exact same way as we did with the most simple example, but then before we actually draw the color information, we're doing the opposite thing. If we're drawing from the second half of the tile pattern data, then the next byte will be the color information. But if we were doing the first half of the pattern data, the 4 bytes we've drawn to the screen, that byte that immediately follows will not be the color information, it will actually be another line of bitmap data. And so in that case, we are moving past the remaining 4 bytes by incrementing the stack pointer here, so that the next byte that's popped off the stack will be the color information byte. So that's what's going on there. Pretty straightforward. We've got the fill tiles, these solid colors here, including that weird flashing one. The flashing freaks me out, I don't know why. Anyway, so what we do for that is, before we were just using the tile number as is as an offset, but this time, because we are mandating that the pattern information is 2 bitmap bytes and 1 color byte, we're actually multiplying by 3 here in the same kind of way as we did before, via bit shifting and via addition here. The tile number that's read in from the BC tile map is actually the tile number times 1 for these custom tile, for this fill tile, and so we're effectively here multiplying it by 2 here, and then we're effectively adding the times 1, and that gives us the tile number times 3. But then all we're doing is we're popping 2 bytes off the stack. We're using those for alternate lines. All of the lines are using the same 2 bytes, and then that fill routine will pop 1 more byte off the stack and use that as the color attribute. So there we go. Then the final kind of tile though is the transparent one, the empty tile so-called. So as I said last time, in case you didn't see it, basically value 255 here is a completely empty tile. Our characters sometimes don't fill the entire that Yo80 character there around the feet. It has no tiles being drawn, so those are completely empty tiles, and that is defined by a value of 255 in the tile map, and we're checking that by inking A. If we load in A and A contains 255 and we ink it, it becomes 0. That's a very fast way of checking for 255. Again, it's all about the shortest path possible to returning, basically, in that case of that transparent, that completely empty tile. If it's not completely empty though, what we're going to do is it must be a partially transparent tile. This doesn't really work very well on the spectrum, but basically a byte that's read in from the source pattern data that isn't entirely 0 is not drawn to the screen. Everything else is. Works quite nicely on the CPC, even better on a system like the Sam Coupe. Not so great on the Spectrum, but it's in here anyway. So exactly the same as before, we're multiplying our source pattern data by 9 here. Our transparent byte value here is being loaded into the accumulator, and then we're just popping the data and comparing to that transparent value here. If the value matches, we don't draw it to the screen. In all of the cases, we do, and we set the color byte. So that is that. Now, the reason we're using that value in the accumulator here is you could, in theory, modify that by self-modifying code. If you want to use the byte 0 as something that's drawn to the screen, a value of 101010 as bits might be more convenient, or a value of F0 or something like that. Entirely depends on what kind of graphics data your game is using, but the default for this example is a entirely 0-bit containing value is not drawn to the screen. Anyway, that's all we've got today. Please go to the website, download the source code, the build script, and you know, do anything you can with it. As I would say, you're welcome to use my source code in any way you can. Please like and subscribe and stick around. We're going to have some more tutorials coming later on, I'm sure. I hope you've enjoyed what you've seen today, and as I say, if it was too complex, please, you know, look at the code and maybe just strip out a few bits that you can make use of, or learn from some of the ideas, even if you don't use the code itself. Thanks for watching today, and goodbye.